All right. Good morning, everyone. Thanks for joining this virtual presentation today for the Engineering Day. My name is Terry Young. I'm assistant professor in transportation engineering at the Department of Civil and Environmental Engineering. And today I will be very happy to present some current research and application in civil engineering, which is related to the smart cities. So most specifically, we're going to talk about some smart mobility systems with the smart vehicles, which is also called the connected autonomous vehicles. So firstly, let's talk about what is the smart mobility. So smart mobility is a key component in smart cities. And so when we talk about smart city, we can imagine there's a lot of advanced technology that has been implemented in the cities. And in order to provide a better service to the city residents, the transportation will be a very key component that can greatly affect our daily lives. So smart mobility is integration of different modes of transportation and infrastructure. And to make the traveling safer, cleaner, and more efficient. And it can also reduce the use of the gas-powered vehicles. And in the smart mobility, we sometimes we also encourage the use of electric vehicles. So as we mentioned, because of the support of advanced technologies, smart mobility often use the Internet of Things. So usually for short is IoT, to facilitate the communication between the modes of transportation and user interfaces and through a wireless network. So we can imagine that the smart mobility would be definitely a multidisciplinary domain that requires the collaboration among civil engineer, transportation engineer, electrical engineer, and computer scientist. So we have many elements that includes the traffic reducing measures, such as ride sharing, bike sharing. So we're quite familiar with that. We use Uber and Lyft and every day, and wireless communication, and real-time data analytics and machine learning used in the autonomous vehicles, and some physical infrastructure like the parking space and traffic signals. So we're going to talk about more applications later on how we can integrate those components or elements together to achieve the smart mobility goals. So cities will use the sensors, data platforms, and software to manage their transport infrastructure and service as a single coordinated system. So this is a general definition of the smart mobility. And now let's take a quick look at the potential benefits of using the smart mobility. The first one is to reduce the fatalities. So even though there are some argument on the benefit of the smart mobility can also reduce the frequency of traffic crashes, but the major benefit is the goal of reducing fatalities in those traffic crashes. For example, if we're using the smart vehicles, we can help to reduce the traffic crash risk and also the rate of fatalities. And second is the mitigate congestion. So we are suffering traffic congestion, traffic jams during peak hours in most cities in the US. So using the smart mobility can also help us mitigate the traffic jams during the peak hours, and then improve the economy and decrease pollutions. So I would particularly mention, talk a little bit about this decrease of pollution. So in the smart mobility, usually we call it eco driving. So that is the kind of a way we're trying to coordinate the smart infrastructure along with the smart vehicles to redesign the trajectory of the vehicles in order to reduce the frequency of the stopping and go condition, and so as to improve the energy efficiency of vehicles. So in that case, we can help decrease the pollution. So later on, we have one application to show how we can redesign the trajectory of vehicles to achieve the eco driving. Okay, so now let's take a look at the smart vehicle functions. Nowadays we can observe. So automotive control, and we nowadays we have a lot of vehicles. They have all kinds of automotive control, such as the lane changing warning and control. And for example, for some car, if you are when you are trying to make lane changing when you are driving, and if there's a vehicle in your blind spot, so then there's a light on your side mirror that you will see a light. The light is on, and that means there's some vehicle in your blind spot, and that gives you some kind of warning. And we also can have some automatic lane changing controls in some advanced vehicle or smart vehicles such as Tesla. So they have this kind of function provided. And the second one is lane keeping. So lane keeping is a extension of the cruise control or adaptive cruise control when you are driving on the freeway, and even you have the changing of the alignment of the roadway, and we still have the function to keep the vehicle in the lane. So which is the lane keeping function. And forward collision avoidance, advanced traveler information. For example, we can get the roadway information from the app and some Q warning as well. So there are so many a smart vehicle function that has already been used in today's vehicles. But now today we want to talk about the future car. So this is a imagination of our future car. So so we can imagine that after maybe 10 years, we can have this fully autonomous vehicle that will be operated on the road. So imagine one day after 10 years, when you get up in the morning and you want to get to work, and you get into your car, you just need to set your destination, and you can even use your voice to control the car. Say, okay, take me to my company. So then the engine will be started, and then the vehicle will pick the best route to reach your company, and you don't need to worry about anything inside. So you can do whatever you want. You can maybe chat with somebody, you can watch a movie, or you can have a teleconference with others. So this is our imagination, and also this is our ultimate goal of developing the smart mobility system along with the fully autonomous vehicles in the future. And now let's take a look at a few terminologies. So you may heard about those, some of them before through the media or any other news. So we have the connected vehicles, automated vehicle, autonomous vehicle, driverless car, self-driving car, smart car, so on and so forth. So now the question is, what are the differences among those different terminologies? Because for some of them, they are even much more close to each other, like automated vehicle, autonomous vehicle. And a lot of people are getting confusing about that. And driverless car and self-driving car sounds like pretty familiar but pretty close to each other. But what are the differences? So we're going to talk about that later. So, so firstly, let's take a look at how does a smart car work. So usually, in order to function the automated driving function in the car, so there are 3 steps: input, processing, and output. So here the input include the drivers. So if we still rely on the drivers, so we have the input from drivers and some pre-made data, including the background map in the vehicle, and some electronic map sensor data if we're using the autonomous driving or automated driving, camera, radar sensor, connectivity data if we are using connected vehicles, and other cars and infrastructures. And along with all of this real-time data, then we have some onboard computer that will be used to process those data. So then we have the corresponding control that will be implemented on the vehicle, including the warning or all kinds of type of control, like the lane changing or acceleration, deceleration, so on and so forth. And now let's take a look at the definition of automated vehicle and autonomous vehicles. So there are 5 levels of vehicle automation that has been defined by the SAE. SAE is the Society of Automotive engineering. So level 0 is nothing. So we have no automation. Everything is relying on the human drivers. And then starting from level 1, we start to use some sensors to help with the driving, and usually we call driver assistance. So in most of the time, we just provide some assistance to the drivers, but we still rely on the human driver to control, to operate the vehicles. And then level 2 would be the partial automation. So for the partial automation, we start to activate some automated driving to control some functions. For example, the cruise control or adaptive cruise control would be considered as a level 2 vehicle automation. So I think everybody is familiar with cruise control. So the adaptive cruise control is an extension of the cruise control. So in the cruise control, you set up a target speed, let's say 50 miles per hour on the freeway, or 60 miles per hour on the freeway. So then the vehicle will automatically drive at that speed and maintain that speed. So that is cruise control. And adaptive cruise control is an extension of that. Is we place a sensor on board, so then the sensor will detect the distance between you and the vehicle in front of you. So when the distance between these two vehicles are less than the target or safe distance, let's say 20 feet or 30 feet, so then the vehicle will automatically reduce your speed. All right, so that is adaptive cruise control. But starting from level 3, we're gonna start to use the system called automated driving system. For sure, it's ADS, to monitor and control the vehicle. So then starting from level 3, it's called conditional automation. So nowadays the Tesla will be considered as a level 3. We have the adaptive cruise control, we have the lane keeping, we have a lane changing, and so those will be the conditional automation, which is level 3. So level 3 is still a human driver based control system. So we can activate the automated driving system, but still we have a driver sit there, and drivers still need to put both of their hands on the wheel, just in case some emergency that cannot be captured by the vehicle, so the driver can take the control back immediately. So that is level 3. And starting from level 4, we're going to call the vehicle autonomous vehicle. So level 3 is still called automated vehicle, but starting from level 4, that will be called as autonomous vehicle. And both level 4 and level 5 will be autonomous vehicle because they will be fully automation. And but the difference between level 4 and level 5 is, for level 4, usually we have to pre-design the routings of the vehicle. So for example, you set up a routing from your home to some place in your community, and usually that distance cannot be too long because the level 4 is not that reliable. So usually we use the level 4 autonomous vehicle to maybe send, for example, we can operate that in the campus. We can send the student from one building to another with a fixed route. Then we can use the level 4 autonomous vehicles. But the ultimate goal is to go with the level 5, the fully autonomous vehicle, which will be the one showing in this figure. So this is our ultimate goal, the level 5 fully autonomous vehicles. And nowadays we have already achieved the level 4, and there's a couple of level 4 autonomous shuttle has been demoed and testing in different places of US. So we're gonna go through one example later. Okay, so this is the overview of the ADS, the automated driving system. So we have all types of sensor, onboard sensors like LiDAR, camera, mobile eye, so on and so forth. And so this is the summary of all commonly used sensors for different type of vehicles. But for some vehicle like Tesla, they don't have LiDAR sensors. They basically rely on the cameras. So that's why the Tesla is kind of affordable compared with other autonomous vehicles that are using LiDAR sensors. So I can give you one example. So in one of the projects, we're proposing to build up a level 3 automated vehicle by ourselves. And the overall budget is about 400K, and we're spending maybe 50K for the base vehicle, but we're spending around 200K for just getting those sensors. So then you can imagine the most expensive sensor among all of those sensors is the LiDAR sensor. So this is also one of the bottleneck of implementing the high automation vehicles on the road. So Tesla is they only use the cameras, so that's why they're quite affordable compared with others. And but you can imagine there's a lot of a deficiency of the camera sensors, because the camera would be affected by the weather condition, the light condition, so on and so forth, right? And once we got all the data from those onboard sensors, then we have the core ADS control algorithm will process the data. So then we're gonna start to either connect to some server or some onboard computer, and then we can do the corresponding vehicle controls. So this is a general process of how the automated vehicle or autonomous vehicle will be operated. Okay, so now let's start to look at a few applications here. So the first case is the AV autonomous vehicle, for short we call it AV lane changing in the mixed traffic. So because when we're trying to operate the AVs in the traffic, in most of the time that will be a mixed traffic. So here the mixed traffic means we have the mix of autonomous vehicles and the human-driven vehicles. So here we use the HV to stand for the human-driven vehicles. So when we have one AV try to make a lane changing in response to the standing surrounding vehicles, and so then the dynamic AV control will need to adapt on certain human drivers. So even when you are driving on the road, you can imagine when you try to make a lane changing, the vehicle behind you, but on that adjacent lane may slow down to let you to make a lane changing, or they just go ahead to speed up to don't allow you to make a lane changing, right? So there's a lot of uncertainties in the human driver behaviors. So one of the key functions is to how we can predict the AV or the HV behaviors so as to facilitate the AV lane changing. So now let's take a look at some field experiment, and along with the simulation we can conduct it in the software. So the left-hand side figure is the video shows when this CAV, so this is a connecting automated vehicle, try to make the lane changing from this lane to the adjacent lane, but the vehicle behind that don't allow the vehicle to make the lane changing. Then the vehicle has to turn back. So let's take a look at this. So this is the autonomous vehicle, and all the other are the human-driven vehicles. So let's take a look at this video. You can see the vehicle are trying to make a lane changing, but the vehicle behind that don't allow the vehicle to do so. So then the vehicle has to turn back. So if in this case, if we cannot precisely predict the behavior for that human-driven vehicles, and then you can imagine there will be a potential traffic crashes. All right, and we can also try to simulate that environment in the software, and this is how we did a lot in transportation or in traffic controls. And here in the simulation, we have this blue vehicle is the AV, and still we try to make the lane changing, but the following yellow vehicle don't allow the vehicle to proceed, and then we have to turn back. So until we have a gap to merge in. All right, and this is another example is the Tesla trying to make the lane changing, and at the very beginning you can see now the vehicle turning back, and then until he realized the car behind start to reduce the speed, and we find we have enough gap to merge in, then we merge in. So you can see we try to get left and right, and then left again. Right. So this is what we call abortion and adjustment. So from these two examples, you can see we have a lot of things to do in order to predict the behavior of the human drivers, because we are operating the autonomous vehicle, we are operating the AVs in the mixed traffic environment. And This is a photo of the a demonstration of the level 4 autonomous shuttle that's going to be operated by UDOT. Actually, they have 1 week of operating this shuttle in our campus. So as you mentioned, this is a level 4 autonomous shuttle. So we have pre-designed the route that could connect multiple destinations, and then the vehicle will be operated along with the fixed route. And then you can, from this video, you can see we don't have a driver on board, and the vehicle will be operated by itself. But just for your information, because the current level 4 autonomous vehicle technology is not that mature yet. So this vehicle is actually moving at a speed of 10 miles per hour. It's pretty slow. And now let's take a look at another technology. It's called connected vehicle or connectivity technology. So the vehicle connectivity is we use some onboard communication device, try to get the vehicle connected with either other vehicle or the infrastructure. So here the connectivity technology includes the DSRC, dedicated short-range communication, or the CV2X or 5G. So actually there's a fight between the DSRC and the CV2X nowadays because they're using the same communication channels. And if you're using one, you cannot use the other one. And 5G is also a potential technology that can be used to build up the vehicle connectivity technologies. And once we have those onboard communication devices, we can do the either V2V, stands for the vehicle-to-vehicle communication, or V2I, vehicle-to-infrastructure communication. So for example, V2V means you will get real-time information from the vehicle that is nearby to you. And for example, there's one vehicle in front of you, and that vehicle trying to push the brake pedal, and then that information will send to your vehicle. And the vehicle to infrastructure is we enable the talk between the vehicle and the infrastructure. So for example, if you're driving a connected vehicle toward one intersection, so then the communication will tell you, okay, there's maybe 10 seconds remaining for the red signal light or green signal light. You can get those kind of information. And with the connectivity technology, then we can definitely operate the connected vehicle along with some warning functions. But here, the connected vehicle still rely on the human drivers, but we only provide the data to the vehicle, and the vehicle function will provide a warning to the driver. So that is called a connected vehicle, right? So that is different from the autonomous vehicle. For the autonomous vehicle, we use sensor to detect the environment, and we do the automatic control. But the connected vehicle, we rely on the communication to get data, but we still rely on the driver to operate the car. So for example, we have some forward collision warning, lane changing warning, so on and so forth. And so UDOT has built up, the Utah Department of Transportation has built up a connected vehicle corridor along the railroad road in the Salt Lake County, and that includes, I think, 30 intersections. And nowadays they are operating the, this is called a traffic signal priority control, and they put that for the transit buses, and then it's called transit signal priority. So the basic logic is if we have some buses that are already behind the published schedule, so then when the bus gets approached to the intersection, and the bus will tell the intersection, okay, I'm already behind my schedule. So then the intersection will turn the signal from red to green to allow the bus to pass the intersection. So this TSP, transit signal priority control, has been operated for I think about 2 years along the railroad road. So later on, they implement the same technology to the snowplow trucks, and also provide the signal priority control to the snowplow trucks in order to let the snowplow trucks to proceed the intersections without interruption of the red signal light, and so as to clean the street as soon as possible. So those connected vehicle technology is already happened, and it's already being implemented in our daily lives. And then when we have the combination of the connected vehicle and autonomous vehicle technology, then we have the CAV, connected autonomous vehicle. And this is one example is called a speed harmonization or the platooning that has been operated by the Federal Highway Administration. So they have doing some field tests in the Washington DC area. So basic logic is we have a bunch of vehicles, and all of them will be platooned with each other. So then you can see we have a platoon of vehicles, and the actual distance gap between those vehicles are pretty close to each other. So somehow we are trying to use the wireless communication to connect those a bunch of vehicles and try to convert a set of separate cars into like a real-time train on the or more like a metro on the roadway, and then we can allow a really short gap between those vehicles. And this is another example is we call it trajectory control to try to achieve the eco-driving at intersections, because we can imagine we have so many traffic that will be experiencing the delay, traffic delay or traffic jam at the intersection because of the interruption of the red signal light. And the left-hand side figure shows the trajectory of the vehicle under the normal condition. So you can see that we have those vehicles will be stopped by the red signal light for a few seconds, then start to proceed. And the x-axis is a time and y-axis is a space. So you can, from this simulation, you can see we have a relatively long queue has been built up after the red signal, right? So this is how we can demonstrate the real world traffic condition with the interruption of the red signal. And the right-hand side shows what if we can do a control of the trajectory of the vehicles. We can slow down the traffic a little bit. Then when the vehicle arrives in the section, the signal will be turned from red to green. Then we don't really need to stop the vehicle completely. So we can slow down the traffic at the very beginning, then the vehicle will proceed, will pass the intersection without the interruption of the red signal. And this is what we call the trajectory control. So in this slide, we can also demonstrate this kind of trajectory control in the real world. So again, this is the target connected automated vehicle. So you can see all the vehicle in front of have to drive really fast, and we slow down this vehicle a little bit. And then this is a red signal. All of this vehicle has been stopped. And when we have the CAV arrive at an intersection, the signal already turned from red to green. You can see slow down. So then when the vehicle arrives in the section, then we don't really need to do the completely stopping, right? So in that case, we can help to improve the efficiency, energy efficiency of the vehicles. And this is also what we call eco-driving. And there's also other popular CV applications in the that have been conducted by the Federal Highway Administration under the U.S. Department of Transportation. So this is one of the project I'm working on right now. So we're doing the platooning and cooperative merging and speed harmonization design for the connected automated vehicles, right? And so the current CV control platform is called CARMA, which is developed by the Federal Highway Administration. And they have a bunch of CARMA-based autonomous driving vehicles that have been testing across the country. And the basic overview of the CARMA platform is we have a sensors, and that collecting the data. Then we have the plan stack that doing the ADS control, automated driving systems, and also along with some cooperative driving features. So this is a AV components, and this is a connected vehicle CV components. Then together we have the CV controls. So then we have the ACT stack that providing the vehicle level controls. And this is another automated driving software. It's called AutoWheel, and that has been used by many commercial vehicles, including Toyota. And there's some more to come. So the Federal Highway is proposing to starting to build up this kind of a small car or toy car that can allow us to perform some research in the lab. So this, they call it CARMA 1/10, and the cost of this kind of a small car is about I think it's about $3,000. It's much cheaper than a real world autonomous vehicles. So then you have the same function on board, and you can still do the all type of control in the lab. So they are still building up this product, and once it will be ready, our research lab will definitely get one to provide some in-lab autonomous driving controls. And also they have the CARMA system have been go completely online, and now it's called the CARMA Cloud.